Fluid mechanics is that branch of science that is concerned with the mechanics of fluids and the forces on them. It has applications in a wide range of disciplines, including mechanical, aerospace, civil, chemical, and biomedical engineering, geophysics, oceanography, meteorology, astrophysics, and biology. In the previous video, we discussed about streamline flow and turbulent flow of incompressible fluid. Now here, we have a handful of topics like viscosity, laminar flow, velocity profile, and coefficient of viscosity. What kind of property is viscosity? When a liquid flows in a streamlined manner over a fixed plane surface, it is seen that the layer of the liquid in contact with the surface has no motion due to the force of adhesion. The layer remains at rest. However, the velocities of other layers are proportional to their distances from the plane surface. As the distance increases, the velocity of different layers also increases. Consider two consecutive layers flowing horizontally being pushed along by some pressure from the left. The upper layer is moving with a velocity greater than the velocity of the lower layer. That is, a velocity gradient exists between the layers. When such a velocity gradient exists, there is a shearing force between the layers. The faster one exerts the force on the slower one in the forward direction, while the slower one exerts a force on the faster layer in the backward direction. The tendency of this force, known as viscous drag, is thus to destroy the difference in velocity between the two layers. Unless some external force is applied, the viscous drag will ultimately stop the motion of the liquid. The property by virtue of which a liquid opposes relative motion between different layers of it is called its viscosity. It is a common property of all fluids. Now, let's be familiar with the terms laminar flow and velocity profile. When the velocity flow of a liquid is less than the critical velocity of that liquid, the liquid flows steadily. Each layer of the liquid slides over the other layer. It behaves as if different laminae are flowing over one another. Such a flow is termed as a laminar flow. On the other hand, velocity profile is the surface obtained by joining the heads of the velocity vectors for the particles in a section of the flowing fluid. In a non-viscous liquid flow, there is no retarding effect on the flow. All the layers of the liquid move with the same velocity. The velocities of all the particles at any section are the same. The liquid moves forward through the tube as one unit. On joining the heads of the velocity vectors for the particles in one section, we get a plane surface as shown in the figure. This surface is called velocity profile. So the velocity profile for the flow of a non-viscous liquid is a plane surface. On the other hand, when a viscous fluid flows horizontally through a tube, the layer of the liquid in contact with the wall of the tube has zero velocity. That is, the layer remains stationary. The velocity is maximum along the axis of the tube. The velocity of different layers decreases as we approach the walls of the tube. So the velocity is different for different particles at the same cross section as shown in the figure. On joining the heads of the velocity vectors for the particles in a section, we obtain a parabolic surface. So the velocity profile for the flow of a viscous liquid is a parabolic surface. What is the coefficient of viscosity for a certain liquid? Consider a horizontal layer of liquid PQ moving with a velocity v related to another parallel layer Rs, the distance between the two layers being x. Due to viscosity, a dragging force will act between the layers, tending to destroy their relative motion. To maintain the motion, an external force equal and opposite to the dragging force is required to be applied on the layers. If the dragging force is F, then for streamline motion, Newton proved that the dragging force is directly proportional to the area of each layer when the velocity gradient is constant, and the dragging force is directly proportional to the velocity gradient when the area of each layer is constant. Hence, according to the law of compound variation, the dragging force or the viscous force is equal to the proportionality constant times the area of each layer times the velocity gradient. This proportionality constant is known as the coefficient of viscosity of the corresponding liquid. It depends upon the nature of the liquid. If the layers of the liquid are very close to each other, the velocity gradient v upon x can be replaced with the differential notation dv upon dx. Now, if the area of each layer is unity and the velocity gradient is also unity, the coefficient of viscosity becomes equal to the viscous force. And from here we can define the coefficient of viscosity. The coefficient of viscosity of a liquid is defined as the tangential force per unit area required to maintain a unit velocity gradient, that is, a relative velocity of 1 unit between two layers 1 unit distance apart. In SI system, the unit of viscosity is decapoise. 1 decapoise is equal to 1 Newton second meter inverse 2.